Okay, thank you everyone, and good afternoon. Hope you recovered a little bit from the break. I'm very glad to be here. My name is Shuai Yuan. Currently, I'm the VP Data Science of MediaGamma. Well, first of all, I want to clarify one thing, which is OpenETL. By the name, it suggests it's open, but it's not released yet. That's a goal. But here, I'm more like to introduce the idea and the problems and our solutions to this unique challenge in data processing. So the plan is it will be released at some point this year. So first of all, about us. The company is called MediaGamma, and we are a spin-out of UCL, University College London. It's a university in central London, and we are spin-out of a computer science department, and there is a specialized group in computational advertising research. So naturally, we built on the research works, and we focus on computational advertising and electronic commerce. The company was founded 3 years ago, and we pride ourselves in technology provider in ad tech industry like Beeswax and Telefonica. And currently, we process over 3 terabytes data per day. That's about tens of billions of events. We use these data to solve various problems, especially the bidding optimization in advertising or in real-time bidding, if you know what I'm talking about. The second one is user profiling, and the third one is for electronic commerce use case is building the product knowledge graph, and on top of that, we do various recommendation and optimizations. That's us. And what do we do exactly? I said a few things about use cases in advertising and e-commerce, but to be precise, we can do these. For example, in advertising, we answer a few questions, like, is this fraud? When you have an opportunity of displaying an ad to a user, is that actually a real human user? Because we know up to 40% of the ads are not shown to humans. And on the other hand, about 40% of the ads are not viewed by real humans. So that's a key question on both sides. And also actions. How likely is the user going to take some action for you based on your advertisement? And pricing. How would you like to buy this opportunity? Or how would you like to sell this opportunity? These are all key questions to ask. And also the relevance. How is the end user in front of the screen relevant to my product or to my website? So these are today I will just focus on the advertising use case. So we won't really touch the e-commerce use cases. So just stay with me. To answer these questions, we have developed something what we call the real-time decision making with reinforcement learning capability, or real-time decision engine. We have a deployment which contains a data processing and a model. It plugs in on the intermediaries or with advertisers. It deals with thousands of QPS, and it responds in 10 milliseconds for most of the queries. And what we do we predict the user response, for example, like a click-through rate prediction or conversion or other things. And we also calculate a fair bid price to buy this opportunity, or a fair price as the floor price to sell this opportunity. And we optimize towards a few goals, for example, ROI or CPM, CPA, or we can optimize towards volume or the spend. To solve these problems, it's a general framework to solve a few problems. To solve these problems, we have built an end-to-end pipeline like this. We have raw logs to begin with, and for this raw log, we can augment it with third-party dataset. For example, if you have location and the time, you can have weather. If you know the behaviors of the user on your website, you can use that information as well. If you know, for example, this user is a registered user of your website, of your app, you know what the user has done before, you can use that user behavior as extra feature as well. We call this augmentation in our pipeline, and we simply grab extra features to add into the raw logs, raw data set. Then we join them together. We have a label dataset. Then we do the ETL. For the ETL, we extract the features and transformation, and we probably load it into different machine learning platforms. One artifact from this step is the ETL config. And the data will also be split into two parts, like training and prediction, or training and testing. And then we go through a comprehensive model building and evaluation phase. We select the best model based on 3 criteria. One is the model accuracy, for example, ROC score. The second one is the commercial goals by replaying the logs, for example, the CPA. The third one would be the engineering metrics like latency or the CPU consumption or these kind of things. We select the best one, and we, of course, sometimes it's best many, and we deploy them in an A/B testing framework together with the ETL config. That forms the production deployment. Now today, the key thing is actually in the middle, is that ETL config. Nowadays, we talk a lot about how big our data is and how advanced our machine learning algorithm is and how successful we have deployed model to solve some problems. But actually, in our scenario, dealing with data is the most challenging part. Making sure the data can be loaded into various platforms, into, for example, sklearn, MXNet, TensorFlow. They are all different formats. They don't recognize the raw data set. And after the data augmentation, you need to make sure your data is processed the same way in training and in prediction as well. So that's actually a key part that's being largely neglected. So that's the key thing that I want to talk about today. So before that, let me show you some real data snippets. These are raw files and intermediate files from our one of the pipelines. And the left one is the raw input. It's in JSON format. It's unstructured data. I apologize, it's too small, but you can see there are many nested layers with different fields and different keys and values. And the right one is is like a tree walk, canvas. We collect all the information available from the document. Then from that, we have transformations to transform the raw features into the actual numerical features, for example, one-hot encoding or count vectorizer. So this is a typical step in this ETL process. It's overly simplified, but that's the idea. You need to transfer the raw input into features. Now there are a few challenges. The first one is how to deal with the arbitrary fields in unstructured logs. Right? We have seen the raw input data. You don't really know. It's not a structured data source. It's not a SQL table. You can't rely on defining a schema because these schema change every day. New fields come in every day, and values come in every day. And how can you make sure that these can be processed consistently and no new fields are neglected? And how do you know there are new fields? And also, these raw files needs augmentation. For example, the first line is a timestamp. It can be easily expanded to year, month, day, hour, day pass. These are all meaningful features for most of the machine learning problems. And there are also other augmentation opportunities, like, for example, App ID. For App ID, you can have app screenshots, app reviews, app categories, and you can get meaningful embeddings from these things as well. And other challenges include they could be deep nested, and there could be multiple items in the value, which requires a splitting by some separator. And some fields, they simply need to be dropped. Now, that's what we call the challenge is the arbitrary fields. You need to do arbitrary things against arbitrary fields. The second challenge is how can you guarantee your feature extraction and augmentation that hold consistently in training and in production, in test, in many, many different environments and systems. For example, the user agent parsing. Maybe it's too small, but in one case, it's parsed as family Windows, major 10. In other case, it's parsed as family Windows 10, major none. So these are subtle differences, but it can be a huge headache if it happens on important features, like hashing, for example. The next challenge is on making the ETL process portable. Like everyone here, we do our data processing heavily in Spark. And Spark is a very, very nice, very brilliant distributed cluster system, but it is a cluster. You can't run that, well, at least for our case, you can't run that like in production. You have to have a single instance running the prediction or the inference code only. So we will need to make sure this ETL process is portable. What we do in training needs to be able to apply it in prediction as well. So here, you can see we have two parts of ETL. One is what we call the common ETL. Another one is a model-specific ETL. We expose an HTTP endpoint in the online stage, and when we see a payload decoder, we use the payload decoder to translate the incoming payload, data payload, into the, for example, Python object. Then we run the common ETL on top of that. Then we split in the A/B testing framework, we can split by random numbers or by user IDs or using multi-arm bandit. And these splitted traffic will go to model-specific ETL, then go to specific models. Now, there are many different small ETL steps for every model, for every branch of the model. So making sure that is exported consistently and run consistently is also crucial to us. The next challenge may be not so important in most of the cases, but it is surely very important to us, which is how to run it fast enough. Well, if you imagine, if you consider that when you are dealing with hundreds of thousands of QPS, and for every request, you only have 10 to 15 milliseconds of round-trip time, and consider the overhead for API, for decoding, for HTTP endpoints, and you also need to make sure that you are running this fast enough and cost efficiently. Now, all these things combined together, it becomes a very, very difficult engineering challenge. So it's common, well, I want to comment, it's common to implement the prediction functions in a different language. We all develop in Python, but actually sometimes it's easier to implement the prediction in Go, for example. That's one thing we experimented. Trying to address these challenges, we have developed internally a package, what we call the OpenETL. The OpenETL has these functions or these features. First, it can do tree traversal. It has a recursive function to traverse a Python object, to traverse the tree, to get as many features as possible. And it is built as a library, so it can be used. Well, we built multiple libraries for multiple programming languages like Python and Go, but down to the under the bonnet, it is actually configurations. We don't write code to do ETL. We actually write configurations to do ETL. I'll show you a sample afterwards. And also, we use the microservices architecture. We containerize the common ETL layer, the model layer, the I/O layer, and we also containerize the experiment control. So in this way, we guarantee that the thing we do in ETL will be consistent across environments. Now, before I jump to how we exactly do this, let me introduce you a few alternatives. There are a few very clever tools for feature engineering or for general ETL purpose. The first one is the feature tools. It's a framework to perform automated feature engineering. It's very brilliant when you have all the data ready and the data are connected. Then it can extract the temporal and relational data set into feature matrices for later machine learning. So you don't need to worry about getting data out, and you don't need to worry about building interesting conjective features. It can simply work. But for us, well, it's limited to be run on data sets that can fit into memory. And in our case, it's simply not enough. The second one is from Salesforce. It's Transmogrify. Transmogrify. It's an end-to-end AutoML library written in Scala and built on top of Apache Spark. The idea is actually getting very similar, getting very close. But For us, it's not enough that we can't export the thing from this thing into our own production environment. That's the main limitation. And the next one is the Bonobo. It's also a very interesting framework. It's for Python 3.5. It's very lightweight. You can define your own operations in this framework. But to us, well, I think it's kind of similar, and we don't know how, well, down to details, I'm not exactly sure how we can compare with Bonobo, but we know that this is one option. To be honest, probably in future we'll consider try to make use of Bonobo, this framework, because we checked out it's really lightweight. It supports a lot of operators, but for now we just keep it separate. Now back to our own tool, the OpenETL. What can we do? In OpenETL, we define a few things. We define a few stages, and in every stage, there are operators. The first stage we define is usually data loading, but that's not interesting. The second stage is usually extraction. For extraction, we define we can support these operators like object transverse, split, exclude, augmentation, and evaluation. Just to be clear, this augmentation can support internal and external data sets or data sources. For internal one, it will be loaded into memory. For external one, it will query an API following some specification. And for evaluation, it's literally just running whatever you write, like eval function from Python. But it's very useful for some specific cases for doing feature transformation. The next stage is usually augmentation. When you have raw features from the raw data set, you usually want to do something to make it, better, bigger, the data set. For example, we can do doc2vec for a given data corpus. If it's text, we can apply the historical click-through rate or conversion rate or of an app or of an user or of a website or even of a placement or of many things. Then you can have the first-party user data, for example, the abundant shopping cart value. If the value is high, you probably want to spend higher to get the user back. Then, as I said before, you can have time plus location to add in the weather data, which can also influence the sales. The integration of augmentation is, well, we can do load that into memory as a dictionary, or we can, if the data is too big or it's a third party, we can also call the real-time API. The next step is usually transformation. For this step, we support a few things. Well, you may recognize all of them already, like count vectorizer, hashing, and bucketizer, min-max, and polynomial features, which combines all the features, a few features together to form higher order features. For this step, that's actually the real tricky part, because we know for some transformation, it requires you to, to traverse all the data sets before you can do anything. So if necessary, we would train these transformers in Apache Spark. For many transformations, fit is very expensive and very slow. It loads all the data. But once you have fit the data set, fit your dictionary, for example, or transformer, the transform function is actually very cheap and fast. So for us, we train the fit function in Apache Spark, and we save the parameters, and we implement the transform function by ourselves. For example, the count vectorizer or one-hot encoding. Then the next one is optimization. That's one, it's not really a stage or the operator, but that's one thing we consider important. We have higher level APIs for this OpenETL package to manipulate the ETL pipeline steps in every stage. So for example, in the extraction stage, you have done a lot of splits on many different fields, or you have traversed your tree into every depth. But it may not be necessary. You can stop at the first 3 depths, or you can skip a few splitting, or you can skip a few data augmentation. These are all optional steps. If you mark them, then or you give them optional priority, these can be dropped if it found out to be too slow in later engineering-facing performance evaluation. right? So these are all just optional steps. We build a configuration, and for every stage, the steps are actually flexible. They will determine how you train a model, but every time we evaluate the pipeline from the beginning to the end, and we use some heuristics to determine for the next iteration how would it go. For the optimization on the ETL pipeline itself, we use Python for Python, and later we want to add in other languages. Currently, the Golang is on the way, but Java is being considered. Now, with all these, probably it will be helpful if I give you a real-world example by using this library. To solve this problem, well, to use this library to solve this bidding optimization problem, we first need to understand the input data set. It's similar to the one I showed you before, but it's actually has a few, it's messier than that. For this input, it doesn't really follow the industry standards. There's actually an industry standard for real-time bidding called OpenRTB, but this one is more customized. It's defined by the customer. It's mostly text-based. It's in JSON format, and obviously it requires further processing. These further processing includes like doing doc2vec on that URL. You can get the content of the URL, build an index, and apply doc2vec on top of that. You can augment the spot ID and product ID of their historical conversion rate or click-through rate. Then you should split a few fields, for example, video type and the categories. This user category is actually the interest of the user, so it is actually very important. If you just use a category as a raw value, it simply won't work. The performance of the model would be terrible. And also, there is a float value or continuous value, which is a reserve price. We should try to bucketize it before we do any encoding. Then we should also exclude a few fields like IP and ID. Given this data set, we have developed a ETL config like this. And first, we do the feature extraction by traversing the JSON or the Python object. Then we have splitting features, and we have the augmentations, we have exclusions. And for the augmentation, you can see in this case, it's internal augmentation. We simply load the data set into the memory. For this step, we can decide we only want to load the top 100 or top 1,000, the most important items into memory, so it doesn't really blow the memory. Then the last step, the transformation, it is the vectorization by one-hot encoding. To be specific, is implemented by count vectorizer. So this is the OpenETL config file, and we can load this config file up in training and in prediction as well to make sure it works the same. It works the same way. The output of that ETL process could be a dense or a sparse vector. If it's a sparse vector, it has these three features or attributes: size, indices, and values. It can be in JSON or CSV or Parquet format. It has optional label fields if it's a supervised learning problem. And that's the end of the ETL process. And following that, we can do whatever kind of machine learning we want to do. At the moment, we do two things. One is we use a Spark built-in ML library to do the machine learning. Another one is if the data is not too big, we simply use sklearn to carry on. But there are utilities. We have developed the utilities to load the output in this format, translate the output in this format into a sparse vector that can be recognized by Spark or by SciPy or by TensorFlow or by other platforms. That's the real-world example, and I hope it makes the things clearer. That's everything I want to talk about. Thank you very much. Do you have any questions?